Okay, time for me to concede that holding my phone is a little bit ridiculous and engineer myself a better solution. All right, so moving into manipulating vectors. This particular problem number 1 in this section, is about some hikers who travel on one day 8 miles northeast, on a second day 10 miles west, on a third day 12 miles northwest. We're looking for the net displacement of the hikers from the beginning of day 1 to the end of day 3. First approach, of course, is to draw a picture. So I've drawn in for myself a coordinate system, east and north in their standard locations. The origin, the beginning point for the hiker's hike, is here at the origin of my coordinate system. Notice that absent any further information about where to the northeast, we assume that we're heading due northeast, so exactly halfway between north and east, or a 45-degree angle likewise over here when we head northwest. So notice that this is not a scale drawing. This is merely a drawing to help us understand basically what's going on. If this were a scale drawing, then we could turn around and just measure this line, this red line being the one that shows the displacement from the beginning of the hike to the end of the hike. We could just measure that directly with a ruler. Part of the reason I'm pointing this out is that when you draw a drawing that's not to scale, you can find yourself tempted or attracted by the way you've drawn the drawing. Here it looks like part of that resultant line, the displacement line, actually overlaps with some of their travel. If you draw it to scale, you'll find that that's not true. And I've kind of drawn it in this way that's a little bit sloppy, specifically to create this situation so I can call your attention to this hazard in drawing a drawing. So, some of you turned around and drew in your resultant line and then did some crazy set. Not that I'm criticizing it, because that would be sort of the first thing I would do if I didn't also know what to do first. You went through some crazy trigonometric set of triangle drawing in the hopes that you would find perhaps some triangle that would give you, via maybe Pythagorean theorem, some indication of how long that displacement is. And that's a perfectly natural and reasonable approach, except that, as you probably found, it only causes you to tear your hair out and doesn't actually get you an answer. Or maybe it does eventually, but you tore your hair out and spent quite a bit of time on this on the way. Instead of doing something like that, we're instead going to take a different approach, and this is the approach that I would like to make sure you kind of train yourselves to do whenever you see a vector going off at an angle. Whenever you have a vector going off at an angle, turn around and break it into its component vectors, one which is parallel to some convenient axis of your coordinate system, here parallel to the north, and one which is parallel to the other convenient axis of your coordinate system, here parallel to the east. When you turn around and do that, your approach is going to be that instead of mucking around with all these angled bits, you will have a eastward component, a westward component, another westward component, and you can add them up to get a net east-west running component. And then you have 1, 2 northward components which you can add up. And then taking those summed or net east-west components and the summed north-south components, you can then use Pythagorean theorem and some trigonometry to find out something about the resultant vector. So let's take a look at doing that. For day 1, you have yourself a triangle that looks like this: 8 miles, that angle there. Theta is 45 degrees. This is the opposite side. This here is the adjacent side. In the standard SOHCAHTOA way of talking about trigonometry. So the eastward component here, notice that when I first wrote this up, I got them backwards, is the hypotenuse times cosine of 45. This is because cos theta, this is what I get for trying to write while looking at a camera, so cos theta is equal to adjacent over hypotenuse. Kind of move that onto the screen there. So for the east-west component is 8, the hypotenuse, times cosine of 45 degrees, 5.7 miles. Notice that I didn't turn around and take the 12 digits my calculator gave me. I assume back in chemistry class or physics class or some previous science class, you did talk about significant figures. In general, taking a large number of digits makes little sense because they are digits out beyond a certain point, are not within the ability of someone to measure. So in a strict significant figure perspective, I actually am only entitled to 1 sig fig, but I'm taking 2 just to kind of make numbers reasonable and neat. Okay, so anyhow, the north-south component for this triangle is going to be similar to this situation here. Opposite over hypotenuse is equal to sine theta, and we have 8 times the sine of 45 degrees gives me 5.7 miles. And that is what happened on day 1. So on day 1, while I may have gone 8 miles northeast, what that really translated to was 5.7 miles each of north and east. On day 2, of course, I traveled only west 10 miles, which is really a travel east of negative 10 miles. And on day 3, I once again use a triangle setup to find that I have gone 12 miles at an angle times the cosine of that angle, so 12 miles times the cosine of 45, or 8.5 miles west, or in the east-west positive is east way of thinking about things, I've gone negative 8.5 miles east. And then likewise on day 3, I went 12 times the sine of 45, or 8.5 miles north. That means now that I can turn around and sum up all of my displacements in each direction. In the northern direction, I went 5.7 miles on day 1, 8.5 miles on day 3. Of course, on day 2, I went only due west, so there is no north displacement there, so I haven't added in a 0. Although I suppose to be strict I should have. That gives me 14.2 miles in the northerly direction. In the east-west direction, I went eastward 5.7 miles on day 1, westward or negative 10 miles on day 2, and then westward again 8.5 miles on day 3 for a negative displacement of 12.8 miles east, or a positive displacement of 12.8 miles west. If all that manipulation of sheets didn't make you sick, I don't know what will. Now I have a final sort of triangle that summarizes what I've actually done. I went 14.2 miles north. From my start point, I went 12.8 miles west from my start point. This line here is my net displacement line from my start point here. I can use Pythagorean theorem to find out how long that is. So remember, Pythagorean theorem is the hypotenuse distance squared, c squared in the usual way we talk about Pythagorean theorem. C squared equals a squared plus b squared. That simply now involves plugging some numbers in. We find that c, which is equal to the square root of 14.2 squared plus 12.8 squared, gives us a 19.1 mile net displacement as the crow flies from start to finish. If I wanted, I could ask an angle question. I could say, well, what is this angle from the east-west direction? In order to do that, I happen to know that the tangent of theta, so the tangent of this angle theta here, is equal to the opposite over the adjacent. Once again, SOHCAHTOA. That means that tan theta is equal to 14.2 over 12.8. If you are doing this on a calculator, you use the invert tan button and find that we end up 48 degrees north of west in this problem.